Today's the name of my topic today is the use of hydrogen as an additive to improve the characteristic of low calorific value gaseous fuels, and I think that I will give you a little bit different perspective of using a certain type of the fuel. First of all, I want to emphasize that it is quite certain that introduction of hydrogen and mixtures of hydrogen and low calorific gaseous fuels like biogas or landfill gas for the energy needs of the modern society reveals a number of open questions related to the problems of applying these fuels in the future commercial gas devices. As you know, currently the fuel cells are the only commercialized devices for using hydrogen, and in the case of using hydrogen by the combustion method, there are already commercialized gas turbines, but only for high power. While in the case of devices of the lower power, manufacturers are still in the research and development phase. And because of that, I think that our country is given the opportunity to be in the process of developing technology for the application of the hydrogen in that energy sector. So, a little bit about hydrogen as an additive for the low calorific value gases. First of all, hydrogen can be used as an additive in combustion to increase the energy content of the low calorific gases and improve their combustion properties. And low calorific value gases are gases that have a low energy content and are usually produced from the waste or biomass, such as landfill gas or biogas. As I already told you, these gases are often used for energy production in power plants, but their low energy content and variable composition can make combustion difficult and inefficient. So hydrogen, on the other hand, has high energy content and burns cleanly with no emission of the carbon dioxide or any pollutants. And adding hydrogen to the low calorific value gases can increase their energy content, improve their combustion properties, and reduce emission. And hydrogen can also help to stabilize the combustion and reduce the risk of the flame out, which can be a problem with low calorific value gaseous fuels. However, there are also challenges associated with the use of hydrogen as an additive, and one of the main challenges is that the hydrogen is highly inflammable gas and requires special handling and safety precautions. In addition, the cost of the production and transporting of hydrogen can be high, which can limit its use as an additive. Overall, the use of hydrogen as an additive for the low calorific value gases in combustion can be an effective way to improve the energy content and combustion properties of these gases, but it requires consideration of the safety, costs, and other factors. This principle is applicable to many low calorific gaseous fuels. Here I'm talking about biogas and landfill gas, but also there is a blast furnace gas that we can expect that it is very often used in industry. In the case of the production of the renewable energy sources, the impact of the adding hydrogen to biogas with a lower percentage of the fuel components, and by that I mean methane, is very interesting. And this type of hydrogen use could have a significant impact on the use of existing energy potentials related to the both primary and secondary gaseous fuels at all. One of the ways to achieve the above goals is to develop the fuel flexible, low emission, low cost burner purposely designed and optimized in order to be fueled by the renewable gases, and their blends with the hydrogen. Biogas are usually utilized in the specialized engines to generate power in the form of electricity and heat. The presence of the hydrogen in the fuel can be tolerated by the 20%, according to the engine manufacturers. And although there are some debates about the proper type of the engines and the fuel filling system. It is also needed to be emphasized that Serbia is about to reach about 100 megawatts of biogas installed CFB plants, which is the highest among the neighboring countries. And on the other hand, biogas is less often utilized in households, farming, and similar, mostly in less developed countries using high emissions, low efficient burners, and no hydrogen is expected to be blended with this type of gaseous fuel. I wouldn't be taking so much attention on this, but I just want to say a few words about the hydrogen. As we all know, that is the first and lightest chemical element at the standard conditions of the pressure and temperature. Hydrogen is colorless, odorless, and tasteless diatomic gas, and it is non-toxic. And because of all these abilities of the hydrogen, it is very potent and very good fuel. It is also very reactive element, and because of that, it can be used as an additive for the low calorific fuels. So when we have the burning process, we can say that hydrogen will burn first, and that is the main thing that we are using here. Here also, I don't know if you can see, I can present that the calorific value of hydrogen is very high if you compare that to methane, propane, or the petrol. That is also very important in order to get higher calorific value of the mixture of the hydrogen with the low calorific fuels. So also hydrogen buoyancy as a safety asset is very interesting. Gaseous hydrogen has a density of 0.0838 kilograms per cubic meter at at normal temperature and pressure, which is more than 14 times lower than that of the air, for example, at the same conditions. The specific gravities of the hydrogen and air at NTP are 0.07 and 1.0 respectively, and you can see that on this figure, the density relative to air. You can source hydrogen, methane, and propane, and only then the petrol vapors. So, what are the main obstacles, or not just obstacles? Some thing that we must take into consideration. It is the hydrogen production. Hydrogen can be produced from a variety of sources. And first of all, we have steam methane reforming. Then we have electrolysis, maybe the most popular way to get hydrogen today. Then biomass gasification, thermochemical water splitting, photobiological water splitting. And overall, I can say that the hydrogen production is a critical component of the hydrogen economy and plays a vital role in the development of the clean, sustainable energy technologies. The choice of hydrogen production method depends on factors such as cost, availability of feedstocks, and environmental impact. Main obstacle in hydrogen productions are, first of all, costs. Current hydrogen production methods can be relatively expensive compared to the other fuels. For example, steam methane reforming requires large amounts of energy and produces carbon dioxide, which must be captured and stored to avoid the environmental damage. Also, energy efficiency. Some hydrogen production methods can be relatively inefficient regarding the large amounts of energy input to produce a given amount of hydrogen, and this can limit the socially and economic availability of hydrogen production. To be frank, I must say that energy that you use for the hydrogen production, you cannot gain during the process of the hydrogen combustion, and that is the main problem in using the hydrogen. That is why the mixing of the hydrogen as an additive is very important in order to get a more energy efficient process. Feedstock availability is also important. Hydrogen production methods that rely on fossil fuels, such as steam methane reforming, are limited by the availability of these fuels. Biomass gasification and electrolysis are more sustainable options, but their sociability can be limited by the availability of the feedstocks such as biomass and renewable electricity. Also, we have environmental impact. Some hydrogen production methods can have negative environmental impact, such as the production of carbon dioxide or other greenhouse gases. This can limit the environmental benefits of the hydrogen as a fuel source. Storage and transportation, as I said before, the hydrogen is a highly flammable gas and requires careful handling during the storage and transport. And the current storage methods, such as high pressure tanks or cryogenic storage, can be relatively expensive and limited the scalability of hydrogen and the fuel source. Overall, these obstacles must be addressed in order to scale up hydrogen production and support the development of the hydrogen economy. A few words about types of hydrogen. As we all know, according to the type of the hydrogen production, we have different hydrogen, and we have, first of all, gray hydrogen. This is the hydrogen produced from fossil fuels, such as natural gas, without carbon capture or other emission reduction technologies. The gray hydrogen is the most widely used type of the hydrogen today, and is often used in industrial processes. Then we have the blue hydrogen. This is the hydrogen produced from the fossil fuels, such as natural gas, with the carbon capture and storage technologies to reduce the greenhouse gas emissions. And the blue hydrogen is a cleaner alternative to the gray hydrogen. Of course, there is a green hydrogen. This is the most preferable type of the hydrogen. This is hydrogen produced using renewable energy sources such as wind or solar power to electrolyze water into hydrogen and oxygen. Green hydrogen is a sustainable and zero emission form of the hydrogen that has great potential to reduce the greenhouse gas emission and support the transition to low carbon economy. Now, the next type of hydrogen is brown hydrogen. This is the hydrogen produced from the coal using the gasification or other technologies. And brown hydrogen is not widely used today and is considered the less sustainable alternative to the gray hydrogen. And finally, we have Turkey's hydrogen. This is the hydrogen produced from the natural gas using methane pyrolysis, a process that produces both hydrogen and solid carbon as byproducts. And Turkey's hydrogen has the potential to be low carbon form of the hydrogen if the solid carbon can be stored and utilized in the way that avoids greenhouse gas emissions. Now, here on this slide, you can see this rather small. You can see the production of the hydrogen and the usage today, blue, green, hydrogen, the most common process for hydrogen getting is electrolysis and electricity demand for the green hydrogen on the lowest level of this segment. Now, hydrogen as a commercial and in commercial and residential appliances. That is also the question. If instead of being injected directly, some hydrogen is allowed to blend with methane and injected into the system, a major immediate safety concern would be the impact of that hydrogen on the customer and commercial appliances, given the challenge and inertia of requiring changes to end use appliances. Any changes would likely be introduced slowly as the blend percentage of the hydrogen increased and as changes become necessary. Even so, adaptation of new appliances would likely be phased in over a very long period of the time, given the low rate of the appliance turnover, 10 to 25 years at least. This is likely to be the greatest practical restriction on adopting high concentrations of the hydrogen, and by high concentrations I mean at least 30% in the gas pipelines. Here we can see that today we are using hydrogen for very few things. It is possible to power our vehicles, and that is the hydrogen that we gain from the process of electrolysis. So, mixtures of the hydrogen and natural gas. Well, the mixtures of the hydrogen and natural gas can be used as a fuel source for the combustion, which can offer several benefits. Natural gas is widely used and easily accessible fuel source, while the hydrogen has high energy content and produces no emissions of the carbon dioxide and other pollutants. When combined, those two gases can create a cleaner and more efficient combustion process. However, there are also several challenges associated with using mixtures of the hydrogen and natural gas for combustion. One of the main challenges is that hydrogen has different combustion properties than natural gas, which can affect the performance of the combustion process. In particular, hydrogen burns at a higher temperature and can result in a higher NOx emission if not properly controlled. To address those challenges, several strategies can be employed. For example, the ratio of the hydrogen to natural gas can be carefully controlled to optimize carbon performances and minimize emission. Additionally, combustion systems can be designed to account of the differences in combustion properties between hydrogen and natural gas. The use of the mixtures of the hydrogen and natural gas for combustion can offer significant benefits in terms of energy efficiency and reduced emissions, but requires careful consideration of the combustion properties of both gases and the design of the combustion system itself. The physical effect of hydrogen addition in natural gas. First of all, we have density and vapor pressure. Care must be taken in the choice of the amount of the hydrogen in hydrogen and natural gas mixture, and that affects significantly the density of the vapor pressure of the gas. If the gas density is reduced, the amount of the hydrogen should be chosen according to the properties of the mixture. Gases with a lower density and higher vapor pressure could better fit in higher amounts of the hydrogen in the mixture with the natural gas. Also, lower explosion limits of such a mixture is very important. Gas mixing in the most countries is under legal regulatory requirement that specified natural gas in air has to be already detectable at the concentration of 20 to 25% for the lower exposure limit. Hydrogen and natural gas have almost the similar LEL values, so the LEL of the mixture doesn't change significantly when hydrogen is injected. And here the simulation I can to calculate LEL of the mixtures in two natural gases. First is the Russian type, the second is the Algerian type, and the data are calculated in reference to the atmospheric conditions of 101.3 kilopascals and temperature of 20 degrees centigrade. So, if you are talking about the hydrogen and natural gas mixtures, the different countries has their own ways. For example, in France, an experimental project called GRID are conducted in 2014, and they are injecting progressively hydrogen up to 20% in concentrations in the natural gas in a local, new and dedicated natural gas grid. In Germany, for example, several injections of the hydrogen with concentration only up to 2% into natural gas are done near Hamburg and in Frankfurt. They are injected those mixtures directly in the local grid. In Italy, up to now, in Italy, there are no injections of the hydrogen into natural gas grids. Anyway, they were done some experiments in 1983 where they have the composition of the manufactured gas, and here you can see the composition of that gas. They have 45% of methane, 98% of hydrogen, carbon monoxide was 8%, carbon dioxide 8%, oxygen 2%, and the nitrogen was the rest. In the Netherlands, in order to state if increase of hydrogen concentration can affect the effectiveness of the gas mixture, they did some research, and they use 3 different concentrations, so 15%, 85%, and also pure hydrogen. In the United Kingdom, they didn't experiment with the mixtures of the hydrogen and the other gases, but they have been using the pure hydrogen as fuel for their appliances, and they release the pure hydrogen directly in the grid. So, here are the mixtures of the hydrogen and landfill gas, and landfill gas has great potential as fuel, and I must say that and I must say that that is very similar as the mixtures of hydrogen and natural gas. Landfill gas is a low calorific value gas that is generated from the decomposition of the organic waste in landfills. It typically contains 15 to 16% of methane, with the remainder being made up of the other gases such as carbon dioxide, nitrogen, and trace amounts of other gases. However, as with mixtures of hydrogen and natural gas, there are also challenges associated with using mixtures of hydrogen and natural gas for combustion. One of the main challenges is that natural gas composition can vary widely depending on the age and composition of the waste being decomposed. This can make it difficult to control the combustion process and optimize the performances. And additionally, hydrogen has different combustion properties than methane, the primary component of the landfill gas, and this can affect the performance of the combustion process, and the result is increasing of NOx, such as the problem with the mixtures with the natural gas. And similarly, to address these challenges, we must have a careful control of the hydrogen to the landfill gas ratio that we need, and overall the use of the mixtures of the hydrogen and landfill gas for the combustion can offer significant benefits in terms of energy efficiency and the reduced emissions, but requires careful consideration of the composition of the landfill gas and design of the combustion systems. Very similar are the situation with the biogas mixture with the hydrogen. It's very similar to the landfill gas, but biogas typically contains around 50 to 70% of methane, with the remainder being made up to the other gases such as carbon dioxide, nitrogen, and the trace amounts of the other gases. The addition of hydrogen and biogas increase its energy content and improve its combustible properties, and this can this can result in more efficient and cleaner combustion processes with reduced emission of the pollutants such as carbon monoxide and particulate matter. However, as with the mixtures of hydrogens and other low-calorific value gases, there are also challenges associated with using mixtures of hydrogen and biogas for the combustions. And one of the main challenges is that biogas composition can vary widely depending on the feedstock and anaerobic digestion processes used, and that is very similar to the landfill gas. Additionally, hydrogen has different combustion properties than methane, and for that, this can affect the performance of the combustion processes and result in increasing of NOx. And in the same manner as before with the landfill gas mixtures, that can be taken care of with the controlling of the hydrogen percentage inside of the mixture and with the proper design of the combustion system itself. So, what are the main obstacles when we are using hydrogen as an additive for the low calorific value gases? First of all, safety concerns. Hydrogen is highly flammable gas, and proper safety measures must be taken to ensure safe handling, storage, and transportation. Also, there is the cost of the hydrogen production. It can be very expensive, and the cost of the producing and transporting hydrogen can be prohibitive, especially when compared to the other fossil fuels. Compared to the other fuel sources. Infrastructure also is very important. Think the existing infrastructure for the storage and transport of the hydrogen is limited and may need to be expanded to support of the widespread use. Combustion properties. While hydrogen has many desirable combustion properties, it can also affect the combustion characteristics of the other gases and may require adjustment of the combustion process when you are introduced to the combustion system. Then you have carbon emission. While hydrogen burns cleanly and produces no carbon emission, the production of hydrogen can be associated with the carbon emission depending on the source of the hydrogen we have. We have the clean green hydrogen, or, for example, we use the gray hydrogen. And of course, regulations. There may be regulatory hurdles associated with the use of the hydrogen as an additive for low calorific value gases, including the safety standards, emission regulations, and other techniques. Overall, these obstacles must be carefully considered when evolving the feasibility of and benefits of using hydrogen as an additive for the low calorific value gases in combustion. So, what are the main benefits when we are using hydrogen as an additive for low-calorific fuel? First of all, increase of energy content, as I already said, then reduce emission. Hydrogen combustion produces no carbon dioxide, that's very important, and can significantly reduce other emissions such as particulate matter, for example, and carbon monoxide and nitrogen oxide. This can make the combustion process cleaner and more environmentally friendly. Then we have improved combustion stability. Adding the hydrogen to low calorific value gases can improve combustion stability by reducing the risk of the flame extinction or instability. This can improve the overall performance and reliability of the process itself, and reduces the fuel costs. Adding hydrogen to low calorific value gases can reduce the amount of the fuel needed to achieve the given energy output, which can lower overall fuel cost. Additionally, hydrogen can be produced from the renewable sources, so using it as an additive can support the development of the renewable energy technologies. And overall, the use of hydrogen as an additive for the use of hydrogen for the low calorific value gases in combustion can offer significant benefits in terms of energy efficiency, reduction of the emission, improved combustion stability, and lower fuel costs. So, improved combustion stability by the adding of hydrogen in combustion gas mixtures can be reached in several ways. First of all, it widens the flammability limits. Adding hydrogen to the combustible gases mixture can widen the range of the fuel flare ratios over which the mixture can be burned. Then increasing the flame speed. Hydrogen has the high flame speed compared to the other combustible gases such as methane or propane, for example, and this can help to stabilize the flame and reduce the risk of flame out or flashback in the appliances. Then we have reducing ignition delay. Hydrogen has the lower ignition delay time than other combustible gases, which means that it ignites faster and more easily. And this, of course, can help to stabilize the flame and reduce the risk of incomplete combustion processes. And that has impact on emission, of course. And enhancing heat transfer, the addition of the hydrogen to the combustible gas mixture can enhance the heat transfer in the combustion processes, leading to the more complete combustion and higher combustion efficiency. I will try. So here today you can see the dedication, dedicated production of the natural gas, coal, and oil that can be used for the demand for the pure hydrogen, and also we have the by-production of hydrogen from the other processes. And that kind of the hydrogen we almost always use for the hydrogen mixing with the other gases. Thank you for your attention. I'm sorry for such a brief in my presentation, but the last one.
Questions? Just the ratio of the price. For example, you could mention 3 kinds of hydrogen production, green, etc. So what's the ratio between from the natural gas production, from the source?
Right now, the production of the green hydrogen can be 2 to 3 times more expensive than the other types of hydrogen. Why? Because for example, if you want to use the wind power for the hydrogen production, it is expensive by itself. And also the efficiency of that method of the power production is very questionable. from time to time. It depends on
Really?
the weather.
Okay. This your presentation is part of some project?
Yes, it is part of the project that we hope that will be financed by our ministry, and also we have some independent studies. Right now, we are working on some experimental work. My colleagues of mine and researchers down there in the laboratory and trying to put some new. How can I say, some new test rig in progress.
So it's related also to some company like PVC?
Right now, not for now, but we hope that we will achieve that.
Okay. Thank you.